Hello everybody, welcome to the Geo Shed. Here is that hypothetical cross-section I have mentioned in other Geo rants. There are prequels or introductions, if you will, to this episode of the Geo-Files linked below as Geo rants. I don't put stuff up here, I find that extremely irritating. Alright, so watch those first. I did that in order to keep this from being the length of a full feature movie. Okay, so watch those first. Geo Rant 115 and 116. Those I explain the framework of what I'm trying to demonstrate here. We are going to see relative dating and absolute dating in this episode of the Geo-Files. Alright, let's get started. Okay, so here we are. First I'm going to cover relative dating. I'm going to use this cross-section, which you've already seen, but I'm going to put slides over it because if I would have drawn on this as we went, this would have got ridiculously busy. You're going to see that from the slides. I just want to say something first before I get going here. These drawings, these are all geologic units, all right? This symbol here that you see here, here, and here, these hatched lines, that's granite. We're going to use that for granite. These circles that you see here, in this layer, here, and here, that is conglomerate. In this case, it's actually metaconglomerate, okay? These thick dots are quartzite, okay? These smaller dots, it's hard to see on here, but these smaller dots in this unit here, here, through here, over here, and up here, those are sandstones, okay? This unit right here with the lines going like this, over there too, here, 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 that is a basalt. It's a surface flow. And I'll get into how we know that when I get into the strat columns. This horizontal dashed stuff here, which kind of turns as we get near this fault here, comes up there. That's our slate. Where it says BIF, banded iron formation. Okay? The brick-looking stuff, that is our dolostone. This long slender thing here and this here with these squiggly vertical lines, that indicates gabbro. And these are our faults. Faults, thick lines with arrows. Alright, let's get into this. Let's get into relative dating first. Okay, I've already gone through Steno's laws with you. Well, we developed this hypothetical cross-section based off some field mapping we did. Okay? Hypothetical field mapping, we generated this. And we're going to use Steno's laws to develop a conceptual model, a stratigraphic column. And we will do this for relative dating too to see if they cross-check. Now, when we develop a stratigraphic column, I need to say something about that. The stratigraphic column is not the same thing, and you see the link below in the video below, as the geologic timescale. There is a certain group of people out there, who remain nameless, who take the geologic time scale, take the word geologic, drop the time scale, take the stratigraphic column, drop the word stratigraphic, and put those two together to make geologic column, which is a term geologists do not really use, because they are not the same thing. They are closely related to one another, but they are not the same thing. But anyway, I digress. Let's get into this. All right, so you see this is our cross-section we've done. I need to point this out, not to scale. We'll say for the sake of argument, that way's north. It doesn't matter because this is a demonstration. This is a model to demonstrate a concept to you. Okay, here are Steno's 4 laws again. I've already gone over them. I'm not going to hit them again, but that's just so you can see it so you know what I'm talking about. We're going to have 4 main types of events in this cross-section. We're going to have deposition of sediments, erosion forming angular unconformities, fault development, and intrusions forming nonconformities. As you can see, there's 2 colors here, red and yellow. Red is going to be used for actual physical rocks being either deposited via sediments or as intrusions, okay? The yellows are our, what I'm going to call mechanical events. Erosion, faults, things like that. So you're going to see 2 colors, red and yellow, as I go through this with you, and based off our cross-section we made, we are going to assign relative ages. What do I mean by relative ages? Well, we have no way to absolutely date it because we're not doing the radiometric dating yet. We are going to use Steno's laws to basically decipher which layer came first, second, third, fourth, fifth, sixth, seventh, and we're going to put the events in between there, the unconformities formed from erosion and fault-in. Okay, so what you see here first is you see these red lines. These red lines represent our unconformities. You see a thick one here on top of our granite. You see two more around our gabbros. Now, off to the lower left here, you see a dashed red line. It is not solid. Why is that dashed? Because we know we have an unconformity there. But we have an unknown question which Steno's laws cannot answer for us that radiometric dating will be able to. We do not know from what we observed in the field whether the granite is older and intruded into our metaconglomerate, or our metaconglomerate was deposited on top of an erosional unconformity that formed on top of the granite. We'll say, based on what we observed in the field, we have no way of knowing. We don't have like a paleosol on top of the granite or anything like that. We don't have inclusions of the metaconglomerate inside the granite that would be able to answer that question definitively. So when we develop our model, we're going to default to the simplest. And I'll get to that here when I get to the numbering here. But before I get to the numbering, up here, you see this blue circle. That's going to come back, because we're going to find something out from the radiometric dating that we're going to do here in the second part, another situation that we did not recognize in the field. But we'll just leave that for now. For now, we're just going to assume that that dolostone is conformable with that sandstone, and that our dolostone thins and pinches out, and the sandstone thickens. And this way, the sandstone, using our law of lateral continuity, if there was no erosionary surface, the sandstone should thicken this way. All right. So remember, it is okay to make assumptions in science as long as they are based off something and somebody else can test those assumptions. All right. And that's what we're going to do here. The radiometric dating is going to be our check for a lot of this. All right. So assumptions are not a bad, dirty word in science. They are if you're just pulling stuff out of your hind end, but then you're not doing science. If you can't test it, you're not doing science. I don't care what your claims are. Now, I can't show that this is older than this or this is older than this right now, but I can make an assumption that can later be tested, and that's fine. Now that I've highlighted the unconformities in red, now you're looking at the faults in green. Now, we have two faults. We have a normal fault down here on the right within the granite. And we'll say we know it's a normal fault because there's a marker bed within the granite, a distinct foliation or something like that. So we know it's not reversed. All right. And we have the bigger fault that cuts the entire section except for the gabbro, which cross-cuts it. And that's going to get into our law of cross-cutting relationships here in a second. Without further ado, let's start ordering, giving a number of events. What happened first, second, third, fourth, etc. Now, it's relative dating, so we're not talking about from the beginning of time to today. We're just working with our cross-section. So number one is going to be our oldest. Number two will be younger than one. Number three will be younger than two, etc., etc. Okay? So based on Steno's laws, number one, I am going to say, is the granite. Now, when you see these numbers, I'm just going to put them on the big part of the unit, off to the main part where they're easily noticeable in the slides here. I'm not going to put a 1 here, a 1 here, 1 here, a 1 here, and a 1 here, because I actually did start doing that. It got too busy too fast, okay? So remember, we're assuming our granite is older than our metamorphic sediments over here, our metasediment. So that's our number one. Now, remember, we are including our mechanical events, our faults and our unconformities, our erosion, okay, and our nonconformities through intrusions. So our number two is going to be this lower right fault. Why is that number two? How do we know that fault formed after the granite? Well, regardless of the relationship with the metasediments, that fault definitely formed after that granite. You cannot fault something that doesn't exist. If this granite didn't exist, I can't form a fault in it. So the fault has to postdate the granite. Well, how do we know the fault didn't occur when this was being deposited, the sandstone? Well, because it stops right at the top of the granite, and we've got a conglomerate on top of it that does not have the fault propagating through it. Now, faults can die out in units, but it is extremely rare that a fault is going to die out right at an unconformity. If this fault was younger than this, it would propagate a little bit, or we'd see some deformation in the beds. We don't have that here. So this fault is our number 2. Now, like I've already covered before, I'm not going to beat this dead horse. Our metaconglomerate's number 3, and our quartzite's number 4. Okay? So after 1, 2, 3, 4 took place, we had an episode of erosion. And number 5 is this hard unconformity that we see across the entire cross section. Now I'm just going to quickly go through the next few so I can get to the other parts. After 5, obviously, our conglomerate and sandstone would be our number 6. This here is our basalt that overlies it, and we know that this is a surface flow, and you're going to see why when I show you the stratigraphic column. I'm going to say it's pitted, and there are distinct reasons why we know that this is a surface flow and not an intrusive sill. So that is number 7, and we will be able to verify that or not through our radiometric dating later. And then we have our slate, which is number 8, our biff, which is number 9, our dolostone, which is number 10, and our sandstone, which is number 11. We have no reason to think it's not. All right, so now we've got all of our sedimentary units down in this model, but we're still not done. We have this big fault right here. This is number 12 in the order of events. How do we know? Because not only did it fault everything except the gabbros, but it formed an anticline here, which I'm not going to show you as a different event, because the compression event that formed this reverse fault obviously formed this anticline and syncline, because based off Steno's laws, they weren't deposited like this. They were deformed. They were deposited level. That's a demonstration of the law of original horizontality. Got it. Okay, now based off our field relationships, we're not quite done. We are going to call both of these gabbros number 13. Why are we going to do that? Because when we were out in the field pounding feet, we found these 2 gabbros. And lithologically, they are identical. They are indistinguishable with the eye, with a hand lens, even under microscope. They look like they're the exact same mineral composition in almost the exact same ratios. So it is perfectly logical to assume that the 2 gabbros were ejected at the same time from the same magma body. And we know that they have to be younger. Well, this has to be younger than at least the basal part of the dolostone. It doesn't intrude all the way through, but it comes close. This intrudes all the way through, so this has to be younger than everything, okay? Because you cannot intrude something that does not exist, just like you cannot fault something that does not exist. I cannot have a magma intrude a bunch of rocks that don't exist. So the gabbro has to be the youngest. And we are assuming these 2 are the same age. Okay, based off of what we just deciphered in our relative dating techniques based off Steno's laws or principles of stratigraphy, they're the same thing. We are going to develop a stratigraphic column. Okay, remember I said we were going to do that? Here it is. This is our stratigraphic column based off what I just went through with you. Okay, we are assuming the granite is Archean on the bottom. And we are going to assume that because say we see a similar granite outside the map area, or we have uncovered it in a previous publication. And they also, and say they have dated it and it came out to be Archean. So we're just going to assume it's Archean, the granite, which is a logical assumption to make based off the available data. Now we have an unconformity on top of that. And later, we're going to have the metaconglomerate and the quartzite deposited on top of that. And we, based off relationships, we are categorizing that as early Paleoproterozoic. Okay, just for something I need to go over real quick here. This here is the geologic timescale we are using for this. All right, notice there's no stratigraphic units on it because it's not the same thing. But we are going to attach a timescale to our stratigraphic column. So what you can see here, the Paleoproterozoic era on the geologic timescale here is divided into 4 periods. They are named here, but for simplicity purposes, I am not going to talk about them because I don't even have them memorized like that. I am going to refer to the Siderian as the early. I am going to refer to the Rhaetian as the early middle. I'm going to refer to the Osirian as the middle late, and I'm going to refer to the Statherian, I'm sorry if I mispronounced those, as the late. And as you can see into the Mesoproterozoic, we only have 3. So I will be calling the Calamaean the early, the Extenian, the Ectasian the middle, and the Stenian the late. This quartzite and metaconglomerate we are assuming are early Paleoproterozoic. We have no other outside data to confirm that or refute that. So that is just based off this here, what we did in the field. Now say above that we have our unconformity, which we clearly have. We're going to call that what formed that unconformity. In order to get an unconformity on top of marine sediments like this or near marine sediments like this, we have to have some sort of uplift. So we're going to tie it into a local orogeny that has been well documented, which we're just going to call orogeny 1 here, which we know, say on based on the literature, is Middle Paleoproterozoic. So we have our early Paleoproterozoic. So we are assigning these to early Paleoproterozoic. And if I just say Middle Proterozoic, I mean the early middle and the middle late Paleoproterozoic, okay? Including those 2 as one. So now we have our sandstone with our conglomerate on top of our unconformity, and we have our pitted basalt above that, indicating that it is a superficial lava flow. And we'll say there's further evidence because the sandstone on top is baked, but this is not baked. All right, and say we know those are late Paleoproterozoic. Okay, or we assume they are based off the available literature of areas outside of where we are. Okay, and we have on top of the basalt, obviously since it's pitted, it was at the surface, there's some sort of unconformity there. It may represent a tiny amount of time or a huge amount of time, we don't know, but it is a recognizable unconformity. So based off everything else we know, the shale, the banded iron formation, the dolostone, and the sandstone, we are going to lump in with the late Paleoproterozoic as well, because, say, we know, based off other literature, we're pulling from other literature, that the general consensus is that this whole package is late Paleoproterozoic outside of our map area. Okay? Now we have our last unconformity, which is by the gabbros, and we are assuming the gabbros are the same lithological unit injected at the same time from the same magma source, so they go on top. And we are assuming they are early Mesoproterozoic. We don't know that, but we are just going to say they are because that's the period right after the Paleoproterozoic. And say we know we're close to, but not too close to, another orogenic event outside of our map area that we're going to call orogeny 2 that may have had a minor influence in this, and say we know that's right at the Paleoproterozoic, Mesoproterozoic line. Okay, so that is our conceptual model. Okay, using Steno's principles, using what we did in the field, and making a picture. And this model makes predictions. All right, that stratigraphic column I just gave you with the names of periods and stuff like that instead of actual dates, or with a general geologic time attached to it. Before we had radiometric dating, the basic principles of geology and laws of stratigraphy were all we had, right? And they were based off of observation. We really had no way to test this stuff until radiometric dating came along, and other techniques as well, like paleomagnetism and stuff like that, geophysics, okay? So we made all these assumptions during Steno's time and through not only the 17th century, 18th and 19th century. Now the 20th century comes along. Radiometric dating comes along. This is a way, this comes up huge. Radiometric dating is huge because it can confirm our principles of stratigraphy, or principles of geology, and our laws of stratigraphy. If we got crazy wacky dates from radiometric dating, that would mean one of three things. That would mean our basic laws of stratigraphy are incorrect, our radiometric dating is incorrect, or C1 and 2, both are incorrect. And we would have to throw the whole thing out. But guess what? Guess how many times that has happened? Spoilers, none. Radiometric dating basically confirmed the laws of stratigraphy. Flat outright confirmed it. Now you can get more data from radiometric dating. Like, remember I showed you we had an unanswered question here. We made an assumption that these two were the same age and that we had a conformity here. We're going to find out we were wrong in a couple of places, okay? That doesn't mean that Steno's laws of stratigraphy are garbage. It was a refinement. Everything else is going to come out to see it's correct, except we'll actually be able to have hard numbers. So we'll actually be able to give actual time frame for what happened off our relative dating, okay? If our laws of stratigraphy and our principles of geology were incorrect and our radiometric dating was incorrect, we would see some stuff. See, because that's the thing. When you're doing science, you have to make predictions. Right? If you do not make and testable predictions, not prophecy, not vague quatrains or crap like that, you have to make actual testable predictions that someone can verify or refute. And if our laws or our dating techniques were incorrect, number one, they wouldn't jive. I just went over that. And number two, we would see different patterns. I did a geo rant below. It's linked. Please go back and see that. I don't want to beat a dead horse here, and I don't want to take up too much time. All right, enter radiometric dating. What you're going to see here is you are going to see dates in different colors. Our youngest detrital zircons are going to be in blue. Why we have a youngest detrital zircons? Well, detrital zircons are pulled from sedimentary rocks. Now, sedimentary rocks are going to have a bunch of different zircons in them. And what's going to happen is when you pull them, you're going to see peaks and valleys. You're going to see peaks of where you get a lot of dates, then nothing, then another peak, which is exactly what we would expect to see if the Earth was old. All right, so, and that's what we see when we get this. Well, why are we worried only about the youngest? Well, because pulling detrital zircons from sedimentary rock cannot give you an actual age. I've gone over this before. What they can do is tell you two things. Those peaks I just talked about, those are going to tell you the source area. That means those peaks are going to tell you where that sedimentary rock was derived from, because sedimentary rocks, by their very nature, are sediments derived from other rocks. So say we date this, we get zircons. This is going to have zircons in it when it forms because it's igneous. The igneous rock is mechanically weathered. It is transported. It's also chemically weathered, but it's transported with the zircons in tow and redeposited as a sedimentary unit. So it can give us a general source area. And I'm just going to give you a little spoiler here. If the Earth was young, no matter where we pulled detrital zircons from, see, you have to make a predictive model or you don't have anything, we would expect to see, no matter what our sedimentary unit is, our detrital zircon should have a relatively even spread from the beginning of the formation of the Earth to today. Not peaks and valleys, okay? And that doesn't happen, all right? So, not only can we get a source area, but we can also get a maximum age. A sedimentary rock cannot be older than its youngest zircon. Why not? Well, because a sedimentary rock, like I just said, was deposited from other rocks. You cannot carry something that does not exist. You can be younger than that. You can carry older zircons, but you can't carry zircons that haven't formed yet. So your youngest zircon will tell you the maximum age that rock could have began to be deposited in. It can be younger. It just can't be older, okay? Then you're going to see this green here, crystalline dates. We are assuming all of our igneous rocks have not undergone any metamorphism. They are undeformed, okay? There's no resetting events, no hydrothermal activity, nothing like that. So they're actual hard dates. You can directly date undeformed, undisturbed igneous rocks, unlike sedimentary rocks. You can get an actual age. And when you see here, with these dates you're going to see, you're just going to see numbers. Those are in millions of years, all right? I mentioned this in another GeoRant, link below, okay? And the abbreviation is MA. I'm not going to include that. I'm just going to include the millions of years. So if you see 1300, that's 1,300,000,000 years. And the reason why we do 1,300 million years instead of 1.300 billion years is because the margin of error on we're going to assume this is all uranium lead dating. Okay, that's the method we're going to use for this. It's just easier, it takes less space to write 1,300 plus or minus 1 MA. Okay, it just takes up less space. It's easier that way. Okay, so let's get into this. Okay, we get a hard date for our granite, which we suspect is Archean. We get 2,741 plus or minus 4 million years. Okay, it's Archean. We pulled detrital zircons from our metaconglomerate and our quartzite. We get 2,300 plus or minus 1 and 2,240 plus or minus 3 respectively. This answers one of our questions, which I'll get into here in a little bit. You can't physically date an unconformity or a fault. These are events. They take a large amount of time to occur. You can only pull dates from the rocks, okay? So you're not going to see a dated fault here or a dated unconformity here. But anyway, so let's get to our, say we take detrital zircons from our conglomerate down here, and we get 1881 plus or minus 2. But then we also take it from the top of the sandstone, from just under the baked zone with our basalt, and we get 1877 plus or minus 2. We have two ages there, and the higher one is younger than the lower one stratigraphically. Our lava unit on top, our basalt, 1885 plus or minus 10. We had a little bit of a big margin of error on that one, and I threw a couple in there like that just to show you how we have to move things around and how we can get better refine things, okay? And we could not do the slate. Say we pulled zircons and they yielded no usable dates, and that happens in finer grained rocks a lot. Doesn't matter if they're igneous or sedimentary, it happens. Say with the basalt, we got lucky, okay? But we have no usable zircons in any of the slate. It happens, okay? But the BIF, say it had a little sand unit in it and we could pull good zircons, we get 1887 plus or minus 9. The dolostone, same thing. A lot of Precambrian dolostones, actually, most of them tend to be siliceous anyway. Say we had a sandy unit or extra siliceous unit in there, a little coarser grains, and we get 1820 plus or minus 13. Now, we get to the sandstone. We get 1499 plus or minus 3 is our youngest detrital zircon. That is way younger than the dolostone. That tells us something. Now remember, we assumed that this is younger, and it still is. It is still younger. Our detrital zircons don't contradict that. But it's not as old as we thought it was. It's a lot younger. There's an unconformity here. Remember that blue circle I showed you? Well, there's an unconformity there that we didn't recognize in the field. So we gained new knowledge, all right? But from relative dating standpoint, we're still correct. The dolostone is older than this sandstone. There's no problem, okay? And we did the two gabbros. Now when you look, this gabbro, the bigger one, big guy, 1489 plus or minus 1. The dike to the left, 1420 plus or minus 5. That is well outside the margin of error. If we have 1420 plus or minus 5 and 1425 plus or minus 2, they would fall within the margin of errors of one another, and we could still assume they were the same event. Well, these are way outside of that, and the spread is what, almost 70 million years. And with the margin of errors, it's a little less, but it's still huge. So these two Gabbros were intruded at different times. And they are still younger than this, okay? And because they cross-cut it. So we can actually get a pretty good age for this. Because even though we cannot get an absolute age when we date sedimentary rocks, here we have something pretty good. We have a young detrital zircon in a relatively thin unit, and we have rocks that cross-cut here that have an absolute date, this Gabbro. So we can kind of narrow it a lot better. And that's what we do. If we haven't, we love, when you take radiometric dates and you're trying to figure out and trying to narrow down sedimentary deposition, we love intrusions like this. They help so much. And the Huronian supergroup, that happens. And that's the real world example I'm going to give you in a future episode. So we have to do a little refining of our stratigraphy here. We don't toss the whole thing out. We basically gain some new knowledge. Our relative dating techniques are essentially correct. We had to make a couple assumptions. Some came out to be true. Some were falsified. So we change our model. That's what you do in science. Models change. Science changes based on the most recent available data. All right, it changes. If this process didn't happen, we would stop doing science. Just because science doesn't seek absolute truth. It develops testable models, hypotheses, theories, all that. I've gone over this before I get on a side rant. If you have any specific questions about that, leave them below. All right, so we have to do a little refining here. So this here shows you how we had to refine things. We now know we have an unconformity under our top sandstone, and we now know that our Gabbros are two different intrusion events. They still could have been from the same magma source, but they're different intrusion events. The big one's number 13, and the dike is now number 14. Now, what do we do with all these dates? Well, we try to see how well they compare to our relative dating techniques. So we add to our lithostratigraphic and chronostratigraphic model slide this stuff here on the right. This is the order of events based off the dates. What you see on the right, the dates, the absolute dates that you just saw me go through, those are on the right here, and they're going to consistently stay on the right. Okay, and here you can see how they compare to our relative dating. As you can see, there's a couple of things that change. Orogeny 2 is now put below the sandstone instead of above it, and we have a decent timing for it now. Okay, other than that, not much has changed. There's no real unconformity between the basalt and the shale. At least we don't think there is. I mean, there obviously is one. It was a surface flow, but it's nothing really obvious and noticeable, so we just took that unconformity out. We could have left it, but we just have no, even with these dates, we cannot verify the length of time exactly, okay? But other than that, nothing changed much other than we got firm dates, other than our Gabbros are now two separate units as well, instead of one, because we have solid dates. So that's what you see here on the right. Now, can we form a time frame, bracket this stuff? Can we sit there and take these dates and get a general time frame for the deposition of each of these units? Yes, we can. All right. Based off those raw dates and our margins of errors, we are going to give these units a time frame of deposition. And that's what you see here. All right, I'm going to drop the relative dating here on the left, and now you just have the stuff on the right. Okay, what you see here is you're going to see three different colors. Orange, those are igneous. That range is just, most igneous things like this Gabbro and this dike would have been deposited essentially on a geologic time scale instantly. But there's a margin of error that we have to consider, so that's why there's a range there. So our igneous units, even though they're undeformed, are still going to have a range to them, and that's the orange numbers. The purple, or detrital zircon range, that is essentially the age range of deposition from when the formation started being deposited to when it stopped being deposited. That's what the purple is. The yellow are our mechanical, what I've been referring to as mechanical, or vents that form our unconformities. You know, we have that tiny little fault. He's on the bottom there. Then we have our first orogeny and our second orogeny. Now, I'm not going to go through this in detail with you. I'm just going to let you look at it. But you can see that the dates on the right, those are the actual, that's our data. The stuff on the right is our data. That's what we collected. The colored numbers on the left, that's our interpretation of the data. Okay? And you can see everything pretty much jives. We just barely had to change our model. There's no really bizarre numbers. Like Gabbro 2 wasn't dated at 3,000 million years ago, because that would pose a huge problem, because you can't intrude all the rocks. You can't intrude stuff that doesn't exist. If any of these Gabbros were 3,000 million years old, well, how did they form before everything else was deposited? How did they intrude stuff that didn't exist? That would be a way to refute radiometric dating. That didn't happen, okay? And it never does, all right? So, what we have here, what has occurred is we have developed two conceptual models, one based off Steno's relative dating and one based off actual lab analyses, our radiometric dating, and the two jive really well. They cross-check each other. They support each other. They back each other up. And this is how you know that they are accurate representations of reality. Are they perfect? Of course not. All right? Nothing in science is perfect. We are not perfect. Our hypotheses and theories are not perfect. That's why they change based on data. And our machines are not perfect. What we use to measure is not perfect. All right? That's why we have things like margins of error. Okay? A machine cannot get us a radiometric dating down to infinity. That's not how it works. That's why we have these margins of errors. So the two cross-check one another. That's validation. So we have one cross-checking the other. They mesh pretty well. We have a good picture of reality. Why would we break it because of some preconceived notion of something that doesn't make any sense? Remember, in science, claims without evidence are claims. All right? You can say anything you want about anything, but in science, if you don't have the evidence to back up your claim, you're just talking. All right? So that is how I did this, to show you how the two methods complement one another. And I will, like I said, in the future, show you a real-world example with the Huronian supergroup. That will be a future episode. So we do have real-world examples of this, all right? And every time somebody does this, we can correlate things better, and nothing wacky comes in and throws the whole thing out, all right? And even if you do take dates and measurements from one little area and say you do get something really weird, you don't immediately throw out the whole of science and go, it's wrong. What we call that is an outlier. You need to first check yourself, check your equipment, check your methods. You don't immediately assume something because you want it to be that way. Analogy of this concept. And this is something I don't understand about people. Humans, when it comes to our technology, we're really good at troubleshooting. Like, if my car doesn't start in the morning, I assume the battery's dead, maybe I'm out of gas, something mechanical is wrong. Something happened either during the night or when I turned that motor off before I got out. I don't assume gnomes and imps came in the middle of the night and started pulling wires. I have no foundation to believe something like that. And if I change the battery and it starts, obviously it was the battery. It wasn't a battery gnome or a battery imp, okay? Those aren't real things, all right? But when it comes to the natural world, we freak out. Like, you know, say you're at a friend's cabin and there were a bunch of you, a couple of them went out to go get some beer or something, and you're sitting there alone by yourself and you hear loud noise out in the woods or creaking inside the cabin. For some reason, when it comes to the natural world, we immediately go to ghosts, aliens, or whatever. I don't know why this is, okay? Or, you know, if you're more rational, you might sit there and go, oh, crap, there's a bear or something like that, or whatever. But the point is, when it comes to the natural world, we fight observations and we fight data for some unknown reason. When it comes to our own creations, we don't. All right, so now I have shown you how Steno's laws have applied over the centuries of a scenario that, a created scenario. I made this up, a cross-section based off hypothetical field work we did, and then we pulled dates and got dates, and the two complemented one another. So now we have an accurate model of reality, all right? So anyway, if you have any questions or comments, please leave them below. I hope you learned something. And like I said, there will be a real world example of this in the near future. So here I am locking the Geo-Shed. And as I go into the house, look who's waiting for me. He gets so excited. It's my son. It's Blackie. His brother. Him a good boy. As long as he doesn't poop on the floor. You ready for me to come in, Blackie? You wanna see me? Oh, I'll be in a second, bud.